Hey, John here. So the other day, I was talking to some people in the Discord about 3.5-inch floppy drives and whether or not you might be able to access one from a Z80 retro project type of thing. And well, one thing led to another, and now one of my PCs is missing a drive. Thanks to everybody that support my channel. I really appreciate it a lot, especially the VIPs listed here. Now, there's a whole lot of detail about these things, all right? Now, I'm not going to go over all the variations and stuff like that. This is a late year model, more recent than the early generation 3.5-inch floppies. And by that, I mean this one can handle the high density disks, all right, and the regular standard density disks, and by that I mean running at 250k bits for standard double density and 500k bits for high density double density. And the way you tell the difference is you look at the disks that you have. Like this one here, it has a single hole on one side and no hole on this left side. This is a 720K disk, a regular double density MFM format floppy disk. This one here is an example with the two holes. You can see this, and I don't know if you can see that well on this camera. I'll get the right light glare to show up on that lens. It says HD, it's like embossed and stamped into the disc right there, okay? So this is a high density disc, and the only difference is that this has magnetic media in it that has a higher coercivity, and therefore you can record bits physically smaller than the magnetic media in here. This is gonna not allow you to record such small little teeny bytes, or bits I should say, or flux transitions is what we're really referring to there. Now the disk drive here should have sensors in it. We can pop this lid open. Let's see if I can get this open. So there's the bottom of the drive. There's the motor is like baked inside this thing. This big thing that spins around right there, the little thumb there, that is a magnet most likely. And this thingy right there, you see that little black chip right there. I'll bet anything that's a Hall effect transistor, and when the magnetic goes by, it can sense each time this thing revolves. That's used as some of the logic that controls the disk. It's called the index, right? So what then happens here when you put a disk in this drive? All right, we're looking at it upside down, so the disk would go in this way, right? So you can see there's a sensor here and another one over there. When you put the disk in there, these are going to see if those holes are empty or not. So the disk went in there and it kind of flipped up in there. These things will sense these two holes, and it'll note that one is blocked and this one is not. This one is a write protect. If it's open, I cannot write to the disk. Put something underneath here so we can see. So this disk is write protected right now. It is solid over there, so it's a 720K. That's why these two lights are in there that detect all this fun stuff, all right? Now, this disk of this era that does all this automatically will internally change its configuration and magnetic, driving power and all that fun stuff to deal with the fact that these two have different kinds of magnetic materials in them, and this one needs more energy or whatever to make the flux transitions smaller than this one here, okay? Older drives don't necessarily do that, and some wonky drives can run at different speeds and all that. This is a very generic one. I don't even know what the brand is. It doesn't even have a brand on it that I found, and runs at 300 RPMs, I'm pretty sure, which is the standard speed. Some of them can go faster at 360, and those are like extra high density. So this regular old disc, cheapest one you could find that was manufactured after the year 2000, is basically this is what you're going to get. Now, in an IBM PC, they have a missing pin. Well, this is the end that goes to a disk. This is the end that goes into the PC. All right, so this is an extra. There's a extra cable here, so you can see there's a corked hole there. So that keys this connector so that people don't put it in, the wrong way around. And the old days, we expected people to actually pay attention to what they're doing. This giant red line and an arrow on the circuit board that says this is your pin 1 here. Well, that apparently wasn't good enough for the yeah. Okay, so that's keyed. The other two thingies in here are not keyed, and there's a twist in this cable here. Again, geez, can you wreck it for the rest of us, people? Somebody decided to increase the cost of manufacturing these cables by requiring them to have this twist in here. And what you'll see why the twist works, but the short of it is, by reversing the order of these pins in this cable, it's flipping around the disk select pins in here. The end of the cable on a standard PC configuration like this is for disk A. This one over here is for disk B. So the straight through part of this particular cable is for disk B. The cable that's in this drive is twisted, and it doesn't have the other cable, the other connector on it, and it has this one that plugs into the board. So there's a single drive cable, and in order to be drive A, you still have to maximize the cost of this manual procedure in manufacture to flip this over. Otherwise, it'll present itself as disk B, and that might confuse grandma or something. Now, this cable, I took the liberty of running over to my neighbor's garage when he wasn't around and grabbed his drill press and drilled out that cork in that hole. That way I can put this on a standard header from ye olde days that does not have the missing pin. And yes, I have to pay very close attention to where this red pin 1 goes, the red wire on here. Okay, so I can now plug this into an oldie-timey disk controller as a 5 1/4 inch drive. And as long as all the timing is set right and everything else, I believe that we can make this disk look to an old controller that I have lying around, make it look like a 1.2 megabyte 5 1/4 drive, because all the timing and everything else is otherwise the same. So all we need to do, as far as I know, is power this drive, compensate for this oddity when it comes to how you control the disk, because in the olden days you didn't do any of this kind of foolishness. You had jumpers and you said you're A, you're B, and so on. And then we could have 4 floppies on one system. With this mechanism, we can only have 2. Thank you very little. Now, you also have to engage multiple bits in this cable just to enable one drive. So there may be some incompatibilities with certainly the firmware that existed back in the old days. I don't know if we can compensate for that with some jumper wires and kind of like cheating this, or if I can just kind of tweak some test code and enable the bits in a different pattern than would normally be used on a 5 1/4 inch cable from 1980. But let's find out. So what are we going to do? I'm going to put in a 720K disk. I'm going to power up this drive. This particular drive, this connector, when I had it open earlier, I looked around inside there and I could see that there's a 5 volt, a ground, and a 12 volt pin on this connector right here. The 12 volt pin is not connected to anything at all. And there's a lot of discs in the later years of 3.5 inch that only needed 5 volts. So we're very lucky. I should be able to just power this up with a USB adapter if I can find a connector that will go on those pins. Now, fortunately, a lot of PCs still come with these power connectors on them. This is for a 3.5 inch drive, and it came with my power supply that's in my desktop system. And it came with a whole bunch of extra cables like this, like black on black, to make everything fine. Now, my desktop system doesn't have a floppy, doesn't even have a knockout to put one in there. and I'm not going to upgrade it in some weird way to have one. So what I'm going to do is just cut this off, and then I have a nice pigtail that I can use. You plug it into a breakout cable or a perf board or something, and connect it to a USB supply. Alrighty. So here we go. Just nip these off. I'm cutting them as close as I can to the connector so that these metal, the leavings here, don't come in contact with metal. If I ever even use this cable will sit in the here. I might need this someday box along with the other motherboard parts from that. It's not going to ever get used. Unless somebody comes along like I am right now saying, gee, I wonder if I can gut a cable out of there. So now I got a way to hook up the power. And it would be really wise if I made sure I hooked it up right. Because you don't want to... It turns out you can't really screw this up. Because ground is the middle two pins. And one of these is 5 and the other one's not connected at all. So worst case scenario, I hook it up to the 12 and it does nothing. Or I hook it up to a 5 and it works fine. All right, so here's the floppy disk controller I want to use. The 5 1/4 inch cable, 8 inch cable. The jumpers on here took me a while to figure out what to do with these things. This board is designed by Calcomp to go along with the CPU card that I've been playing around with in recent videos on my YouTube channel. Now, you know why I was messing with that. So the short of it is, the way this is set up is you've got an empty socket here that you can put custom stuff in it and disable. Shut up, go away. This thing here says, do you want the ROM monitor that's in this EEPROM here to be enabled or not? And with this card in here, this ROM monitor is designed to show up at F000 just like the ROM monitor does in the main CPU board. So what you got to do is disable the ROM monitor in the CPU board, enable the ROM monitor in here, and that's what this jumper here has to do with. This one is set to operate this board at 4 megahertz, and you have to run your main CPU at 4 megahertz if you want to run double density mode, because the CPU can't keep up with the data coming off the disk. I suspect that a 2 megahertz system would keep up with a 5 1/4 inch running at double density, but not an 8 inch, because an 8 inch runs at twice the clock speed of the 5 1/4. We might look into that later, because the 1.4 megabit or megabyte floppies for the 3.5s need to use the 8 inch style clocking, which is okay, except for an 8 inch connector. When you put this particular board in an 8 inch mode, it needs other things, and they don't exist on the drive. If I ever get that far, we'll talk about that later. All right, we'll fake it and it'll go if it works at all. We'll fake it, but I don't know. So it's not going to happen out of the gate. This thing here has to do with helping the CPU run as fast as possible by generating specialized wait states, so the CPU can read from this chip and sit in a wait state indefinitely until this thing provides its data. In order for that to work, you better never read from this thing unless you're expecting it to give you data. So I expect if we're playing around writing some custom code, that may become a bit of a trip up in our plans here. And at first glance, it looks like it's either going to happen. At first glance, it looks like there's no way to really shut it off with a jumper. It's all done through programmatically enabling and disabling and stuff. So we'll have to look more closely at that when the time comes. What's going on in here? This jumper is for like automatic booting, and we do not want to try and boot up CPM by loading it off a disk, because I don't have one for it to do that. This one here and this one here have to do with this coinciding with bank selected memory and all this other stuff, so you can run multi-user mode CPM. Yeah, this is a little bit confusing, but These are how it was set when I got it, and when I read the manual, it looks like it makes sense. This jumper here tells this card to completely ignore all bank selection logic and just always be mapped into memory for this boot ROM at F000, and for all the I/O ports to always be available regardless of what bank has been enabled for the memory. And that leaves us with this boot enable thing. And this has to do with different modes of whether to go into the ROM monitor and yeah. So we want to boot into the ROM monitor. Don't boot up CPM automatically. We're 4 megahertz and we're not doing some custom stuff in here. As far as I know, it's okay. We'll try this and see what happens. And if it works, we'll up the ante and actually plug the disc in. As you can see, all the pins are present on this connector. If you could, I don't know how well that will show up in this thing. If I get the right glare or something. In any event, all the pins are present in this thingy, and that hole needs there, has to be there in order to fit on this thing here. So this will plug into this connector. Now, unfortunately, if you can see here, the cable wraps around here and bulges out the side, and there's absolutely no space for that in here. So I hope I can kind of ram it on. I kind of was trying to fit it on there. I think if we push real hard, it'll go on there. This will maybe bend a little bit, flex it some, but at least this is not a sensitive thing. It's, you know, pretty beefy bunch of pins soldered into through holes. I'm not going to tear something off a surface mount. So I think we can kind of maybe risk it. If it doesn't go, I can undo this connector and redo it so that the cable goes in on the other way and just doesn't go wrap around. It just come right out of this and go in there. All right, so I plugged the card into the box. The disk drive is not yet connected because we need to first kind of get familiar with the new ROM monitor. I was a little bit surprised by something that I saw in here. So here's I bring up the monitor, and if you flip through here, what you'll find is, you know, oh, good, it has the same commands. You can dump out memory. You can remap things to stuff that's disabled with the I/O byte that's not supported. Which is what this is all about, and it talks about the reader and the puncher, and I'm like, okay, cool. Now we got the disk, and I can go ahead and download some code in there with the Intel hex files and the read command like we did last time, except it doesn't have a read command. The read command now only works with the floppy disk, so now we're going to have a chicken and egg problem where somehow we can either interact with a floppy disk or exchange data back and forth there, or we can exchange it back and forth with like Intel hex files. So it's a little bit annoying in that regard. I can't do both, and I'm not really sure how to get over this hurdle, but we do have the ability to manually poke bytes in one at a time if we want, and enter in code that way if we really want to. There is the other possibility that we could fire up a computer with a 3.5-inch disk if we can get the sectors. I mean, I don't know if this thing is really going to work with the same format and sector layouts of a PC disk or not. If it does, in theory, we can create a binary image of a floppy disk and just DD the thing onto the disk and stick it in there and it would go. But I'm not gonna get my hopes up too far. So here's the governing deciding factor here, right? So what is a regular standard PC disk? Because I only have the ability to use this, okay, as interpreted in 1980. And a 5.25-inch double density disk, as I said before, is the same clock speed and bit rate of a 720K floppy disk. Yes, that is true. But I don't remember how big the sectors are. I think they're 512 bytes. in DOS and Windows, which means I do have an option to choose that in this table. So by default, out of the gate, there is some hope that I can read a 720K floppy without anything really fancy going on, because I think this actually is going to be compatible with a PC. It may not, though, because the address marks and other fancy things about floppy disks may not match. I don't know. But I'm going to take a shot at this and just out of the gate. Plug it in, see what happens, all right? That's what we're going to shoot for. What else does it say down here? It doesn't support giant sectors or tiny ones in double density mode. This is mildly nuisance with CPM, because CPM works really well when the block size matches what its native block size is, but I've already done a lot of work with bigger block sizes anyway, so I'll have to use the same technique and map them. On a floppy disk, though, it'll be so slow, it'll be outrageous if we're not careful. So, I don't know. It'd be interesting to see what other people did to deal with the fact that each sector on a floppy disk might have 4 blocks in it from the perspective of CPM. Anyway, what do we got here? So the way this works is you set up, you boot it up, you fire up the monitor, and you use these parameters commands. I scrolled back too fast. You use a P, and you send it some parameters that say which drive I want to talk to. 0, 1, 2, 3, ABC, which disk. Then you say S, which is the, is that the number of sectors? Yeah, that's the number of sectors per track. Now, I suspect we can lie and give it a number that's less than the actual numbers. But if we give it a number that's more, it'll probably sit there trying to read it forever and fail. D, I think, has to do with how many sides. Is it one-sided or double? Oh, that's the density. Number D. Is that right? A single or double-sided? Yes. Disk is 0 for one-sided and 1 for a two-sided. So we need to tell it what? We want like drive A. We want to be whatever this is. What number do you put in there for that? A can't, well, seriously? What is S? Number of sectors. Oh, yeah, okay, it doesn't care what it is. The density or the mode or anything like that yet. Fine, so we're going to give it a 10. We're going to go 0. Probably it needs to be in hex, so it'll probably be A. And then D will be set to 1 for a double-sided disk. Then later on, you give it these parameters that says for the following, like if we want to read something off the disk, we give it the starting information, what track, what side of the disk, and what sector we want to start transferring data at. That's what that's for. And then the R command, which would be nice to still have the other one as well as this one somehow. This thing says, given the current settings of all the stuff I just talked about, transfer data, read data off the floppy, starting at that sector for as many bytes as in this address range and copy it into memory. Okay. I'm inclined to just take a wild swing in it and see what it does. It may require a little bit more probing with scopes and things to make sure that each one of the signals on the board is working correctly, because they're not really compatible. I think the biggest pain in the butt is going to be the way the 3.5-inch disk select thing works, because it's not quite the same as a 5 1/4. So that might be some games there. And then it says make sure that if you want double density, you need 4 megahertz, which I think is really applicable to double density on an 8-inch, because it runs double the clock speed. Okay, and the rest of these commands I think are the same as we saw before. So first thing first, let's power it up and see if we can at least wake it up with the boot ROM disabled on the CPU and the floppy disk controller card plugged in with its boot ROM enabled. You power up the box, hit enter a bunch of times. We have MOS. Wow, we have MOS at 115 too. I didn't set, this is a brand new, wow, let's see what happens. I can't believe this is going to work. Wow. It specifically says it's not going to run at a high, but let's not use this bit rate because it could be problematic. Let's go ahead and choose one that we know works, like 38.4. We need to go 7 bits, which is a U, and we need to be space parity, so the garbage is not on the screen, which is that. Okay. Now I got to reset it and redo the Autobot. There we go. No garbage this time. All right, there we go. Okay. Wow. All right, I guess we're going to plug in the floppy. See if if we can get the thing to select. I would be happy if that works. Let's take a beat here for a minute. This drive is fine and dandy, but it's harder to open up than this disc here. It doesn't even have a bottom, and the top on this pops off more easily. Otherwise, the drives are equivalent as far as I know. You see the two sensors and this thingy here. You can sort of see the head, the track index thingy here, and the sensor. They're equivalent. The cable has this funky bump on the end of it, and I can't get it to go in the card. Forget that. So I made a new one. This one doesn't have that wraparound on there, and it's a straight through cable here, which also eliminates that foolishness with the twist, which, you know, whatever. That's neither here nor there, but I think this will be easier to deal with by a significant margin. And this just goes in now. Okay, that's fine and dandy. The other end still has a lump, which is fine. I don't care. And this one even has a key. The other one wasn't keyed, and the floppies do have this like notch right there. So this is actually probably a better way to even do this. Here we go. A power connector with a USB adapter here for the 5 volts. I'm going to assume that this disc will run on 5 volts like the other one as well. Now let's pull the top off here. Inside, you can see the head mechanism that closes like a clamp on the disc when you push the disc in. And this here is a stepper motor that'll move the head in and out. So we can watch the thing run if we want to. So here's me putting in a 720K floppy. There we go. Well, I'm going to tip it this way when I power it on to show you when this powers up, according to the manual, the floppy card automatically turns the motor on. That's a feature, okay? I don't much care for that right now, but in their defense, the goal, the reason behind wanting that would be because when you power up, you start firing this motor up and the thing can more quickly boot. So there we go. Disk motor on. System booting. I'm going to just set this down now. We know the disk is spinning. And you probably don't want to leave it that way for 3 days. We got to get our software going so we can turn off the motor when we want. Okay, do a little auto botting. There we go. Okay, so let's let's first have a look here. We got to jump around a little bit to get this thing all going. This is part of the schematic of the floppy disk controller from Calcom. And all these pins here these are the 5 1/4 inch connector pins. And you see there's 4 drive selects, 1, 2, 3, and 4. And there's a motor on there. And, step motor in and out and writing the data to the disk, reading it back, and so on. We want to read the front or the back of the floppy, and this is the index mark. Every time it goes around, you get a pulse to let you know the disk spins around, okay? Now, if you go to Wikipedia, they'll give you another set of pins. This is from the perspective of a modern PC, and you'll see all the same stuff in here. They added a disk change pin, which is incredibly useful. CPM did not have that. The ShootGuard SA400, the original 5 1/4 didn't have it. So it had to guess if you ever changed the floppy. We'll talk about that later some other time. It can cause you to corrupt the disk is the problem if the OS doesn't know you changed it. All these other pins are the same. Maybe the names are different, but the places are the same, right? So what do we got? We got, okay, motor enable. Let's look closely at the motor enable Okay, the motor on. This lets you turn on and off the motor. There's only one pin. If you assert this, all drives that are connected to this cable in the oldie-timey days, all the motors would go on at once. And they'd all be on regardless of whether you selected the drive or not. And in some ways that's useful. In other ones it's annoying. But you had no choice. You know, on an IBM PC, you have a choice. You only have 2 disks, but you have a choice. You'll notice there's a motor enable B and a motor enable A. And there's a drive select A and a drive select B. They don't use this pin 6, which is over here, disk select 4. So there's a little different layout here. So if you'll notice, pin 16 here is motor on in both cases, motor on B. And then you got drive select B is on pin 12. Okay, so here is drive select B on pin 12. I don't know if that makes it out on the screen capture here, but that's what it is. You can see the index. You see disk select 1 on the 5 1/4 inch original interface. You got the index here. You got motor A. So it turns out that drive select 1 is abused by the PC to become motor A. Drive select B is still 2, or the second one. Drive select 3 on an IBM PC is drive select A, or 1 on that platform. And of course the motor enable for all the motors in the oldie days is motor B on the PC. So if you think about this, if you use a straight through cable, motor B is the motor on from yesteryear, and drive select B on pin 12 is still the second drive select. It's hard to get drive A to respond to this older interface because you'd have to assert DS1 to turn on the motor of drive A, and then you'd have to assert DS3 to select drive A, which is kind of a weird set of pins to be asserting at the same time. And I would never expect in a million years that the standard firmware on a Cal-Comp floppy disk controller could ever do such a thing. But if you think about the symmetry in here and the fact that they flipped the cable, I'll leave the rest of that thought to the viewer to understand that these are a mirror image and a reusing, abusing of these pins here, which results in this pin layout. Okay, so if we do a straight through cable, my point is this should look like drive B. So if we go to the firmware now and try it out, this is the firmware on the floppy disk controller. What we should be able to do is, let's see here, we looked this stuff up. So these are the registers on the floppy disk controller board, and then it talks you what the registers do. We can actually play around with this, I suppose, with the in and out commands. I should be able to select drive B by simply asserting DS2. Because we don't have, you do have the motor on control here, drive select 2, and I suppose I could also assert drive select 1 and 3 at the same time if I really wanted to. Although we'd have to look more closely at the schematic to see if it actually allows it. I'm sure it does, but I'm sure the firmware that's built in won't do this if we want to use the built-in read commands that we talked about a little while ago. So let's look at the, where am I in the manual here? These are all this. Where's the monitor dock here? It's the cable, the system bus. Here's our funning. Here we go. Writing. We'll get there soon enough. I guess it doesn't hurt anything to try. I mean, I don't care about this floppy disk. Okay, so what do we got? We got various command input. We have move, output. Yeah. Okay, parameters. Here we go. U is the number, the disk number. So we're going for drive B, so that would be a 1. S is going to be, we're going to go sector number 1, because I happen to know that the first sector on floppy disk, in CPM as well as on the PC, starts with 1 for some reason. They don't start with 0. And D being the number of sides, we set that to 1 for a two-sided disk. Okay, so let's go ahead and do that. All right, so let me get that back on the screen here, right? So we want to say P. U is 1 for drive B. S, what did I say S was? The sector number? The number of sectors per track. Oh. We know there's 9 on a 720K PC disk because I Googled it. And they're all 512 bytes. So, and we want a double-sided, right? So that's a 1. Then we go on to the next one here, which is a Q command. It says set the starting track, side, and sector number. That's what I was thinking about for the P. So I say Q, and I go, let's say we want to read track 1. D is the disk side, side 0, the front of the disk, as it were. And then S must be which sector to use. I guess, right? Say S. Hello. S is the sector number in hex. So let's start with sector 1. It'll be the first one. And then you move on to the read command. When you give it an address range, which implies then the size. So if I say read 1000 to, let's say, okay, so if one sector is 512, 512 is 200 bytes in hex. Oopsie, I typed it in wrong. Or 1000 1FF should be 512 bytes. All right, let's tighten up a shot on the drive a little bit and hit enter. Oh, you saw the head move out to the outer track. And I heard it go tick once while it was reading it. And you can see the LED here go on when the disk was selected. And you can see the disk is staying selected. I'm not sure this is a good thing. I know it's not a good thing. You don't want to leave the disk like this for an hour. You want to probably shut it off, or maybe I'll just take the disk out because I don't want to wear down the disk surface unnecessarily. I probably should have done a fill command. Oops. To make sure that we knew what we were recognizing, because we don't really know. Let me do this again. Fill 1000. Let's just read a ton of data this time. It actually worked. I think it worked. I don't know. Let's just go to 8FFF. That's a big chunk of data with 55 in hex. So that's look like that. At least the first sector of data would look in this range here. Okay, so let's go ahead and rerun this command again. Now, I think we have to redo this. I think it picks up where, if I read it again, it'll read another section of the disk. I don't, let's just make sure it's right. Because I think the early sectors are the directory. We should be able to see file names in here. If I just read random areas, I mean, we'll get data, but I won't know what we get. T is the track number, so the track 1. And D, side 0, sector 1. Okay, here we go. Read 1000 through 8FFF. That's a big chunk of data. Put the disk back in. It's still selected from before, by the way. Let's go ahead and see what this does. Made a little sound. Seems to be stuck. I'm not sure it's working. That kind of stinks. I don't know if I eject the disk, if it'll get an error. No. Back in. I don't know. Maybe I think I crashed it or something. Let me hit the front button, reset on the thing, redo this. Okay, let's start over again. Maybe I just messed it up. Maybe we have to do all the settings again. I don't know. Let's go back and redo the P command. Maybe I did it wrong. I don't know. Well, no, the disk got selected. I have faith that this is going to work. What do we got? P, 1 for drive B. What do we say? 9 sectors and double-sided. Let's go back to Q for track 1, side 0, sector 1. And then say read 1000 to 8FFF. Right? See what happens now. Ooh, it ticked a couple of times like it was walking through the tracks. So I don't know what happened last time. Maybe the whole thing's flaky. I don't know. Of course, I just reset the darn thing, and I didn't refill the memory. Oh, that... Whatever. Let's see what happens. Let's see if we got anything that we can recognize in here. Whoa, 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 down there, Hoss. What was all that? Yeah, hey, I think it's working. Oh, baby, baby, baby. Well, that is definitely not random garbage. Crosstalk communicator installation, copyright, yabba dabba dooba. All right, and that coming from a disk. That calls itself the Crosstalk communicator, the installation disk. Oh, wow. No, that's amazing. I wasn't so sure this is going to happen. It works. Wow. Well, let's move on to this guy. I'll bet this. Well, I don't know. Let's find out. Let's reset it and start over again. That seemed to work last time. Wow. Now you'll notice I never set the density when I configured it. And this command, it doesn't say anything about configuring the density here. Well, it is double density. We know that. It just read a double density. It read what it thinks is a 5 1/4 inch double density disk with 500 bytes per sector. That's going to work. Now the problem is if you put in what I just put in a 1.44, the problem with that is that it simply doubles the rate of the data coming off the disk, and it would then look like an 8-inch disk to the controller. And while a lot of these pins are just, the same pins on the 5 1/4 inch interface here and the 8-inch interface, some things are different. Like the 8-inch drive has a special ready signal, where this one does not. So if it tries to, whatever, let's just try it and see what happens. I'm not sure that it's going to work. I don't know. My point is, I'm not sure how equivalent these are and how the firmware, what is it going to do? Just like guess? I guess that's what it's doing, because it was probably also would support a single density disk, and I put a double density. I don't know. Let's see what happens. All right, I hit the front button, redo the autobaud, and reconfigure things. What are we going to do here? I believe it's a P191 was the same thing we did last time. Q101, because even though we're going to go with a higher density disk, what that means is that there's going to be more sectors per track, I think. And I'm lying about that. We may have to put this to, I think there's 18 sectors or 19 on a 1.44 meg floppy. So let's see here. Let's not get too greedy. I heard the head. Oh, it made a noise. Oh. Oh, if you look really closely, what it's doing It's going back to track 0 and then back in 1. So I think it's trying to redo the whole, like it's reseeking. Oh yeah, it died. I don't know what all, that must be track 1, sector 1. I don't know what these mean. Well, like I said, it doesn't shock me too much because 8-inch drives are actually different than 5s. And if you look at the schematic really closely, you see this ready line that comes down here and goes over there, and then it goes down here, and it goes in a gate right there. Let me zoom in as much as I can. Then you see this other wire over here, which looks like an enable on a tri-state buffer whose output is connected to a ready input on the controller with a pull-up on there. So what this is it's true if this gate is turned off, which is the case if this is ever a 1 over here. And if this is ever a 0, it would enable the ready line that comes from the floppy disk, only from the 8-inch interface, okay, to come into and report that the disk is ready to the controller. This other thing here goes over, comes down, and it's hooked up to this pin called Mini Maxi. And in the olden days, we used to call 5-inch, 5.25-inch floppy drives mini drives. I never called an 8-inch drive a Maxi, but I can see why they may have done it for the sake of contrast here. So what has to happen is the firmware has to flip this to do the right thing for the right drive, otherwise this ready won't go on. If you look some more at these two interfaces, you'll also notice track 0 here also is different on the two drives. Track 0 comes over here, comes down there. There's a thing here. Maybe it goes to the other drive. No, it doesn't. It goes over here, comes down here. It's very interesting. These arrows, most of the time on the schematic, the arrow shows the way that signal flows. You'll notice that the arrow's pointing, I would argue, the wrong way here, because we know that track 0 is an indicator from the floppy disk. So this arrowhead is wrong, and it's going down here, and it shows up on another page in the schematic, and it shows up in one of the status registers in the documentation. It says this is track 0 of the 5.25-inch. Now track 0 on the 8-inch does something different. Comes in over here, flows over this way, and then flows down. Oops, I missed it. It's this one right here. Okay, if you don't believe me, we start over again. Here's track 0, Turk 0. Flows over to here, right there, and then it flows down here through a gate that comes in and is joined with another thing with a pull-up and goes to track 0 there. So there's two different track 0s and there's two different readies. And what I think is happening, and we'll have to look at the firmware, which says source at the end of the document. So we're gonna have to pour through that. What I think is going to happen is that the disk type can be determined if you step ahead to track 0 and you look at track 0 going true in the floppy controller, okay? But because these have two separate paths, and only the 5.25 runs over to this track 0 signal here, which if we go to the other page of the schematic, you'll see track 0, where is it? Track O, Turk O, index, head load, motor on, right, track 0 hyphen something that I can't read. Oh, that's two-sided. This is track 0 here. if you come down here and you follow it along, and then it comes down there, it says track 0 on this latch. It's not a latch, 244. So this is a buffer that gates it onto here, which is the data bus, which allows it to flow out to the CPU. So this is the actual physical chip that lets you look at the status of these bits, which show up in this control status, I don't know, what is it, control status 2 or something like that. We were on that page a little while ago. Down here. So what this lets us do, if we want to, that's control register 1, then you have status register 1. That must be status register 2. We've got control register 2 and status register 2. You'll notice it has a track 0 bit and bit 0, which matches the schematic over here, assuming that this one here is in fact bit 0, which it flows through, and it does look like that's the case. So that is track 0, but only for the 5 1/4. My point is that in the dock, track 0 uses this bit to determine whether the currently, when the head is positioned over track 0. Bit 0 will be low for 5 1/4 and high for an 8-inch drive. At the point in time when the head is in fact over track 0, that's a true statement. So, okay, so I suspect that if we pour through the firmware, which I don't really want to do, but, you know, if we want to read these disks, I suspect that what's happening is either we have to hook the disk up to the 8-inch interface so that it knows to use 8-inch timing signals, which is what you need for the 1.44. Otherwise, it's not going to work. And if we look also in the schematic in here, how do you even do that? Huh. Wow. There must be a bit in here somewhere. That's a status register, control, boot, side select, fast seek. Oh, I read somewhere this supports like a voice coil. Somebody must put voice coils on floppy disks so that the heads can move faster. I never seen one of those, but I guess we don't have to worry about that. Where is the control? Is there like a, aha, there we go, 4, mini. 0 in there conditions this for operation 5 1/4. A 1 conditions it for an 8-inch. 8-inch selected on reset. Okay, so I'll bet. Oh, wow. Oh, I don't know if we can do that. This is a write-only register, because if we come back and read a status register, it would be nice if we could see that. Head load, auto boot, no. What's in here? Mini. If we look at status register 2, mini. All right. Does that come from the same place? Here's this. How does mini work? Mini status. Well, we know that. Here's the address lines. Here's the data. Here we go. Mini maxi. Goes over there, comes over here. Okay, so if this must be the register that holds whatever the control for the double density motor on, the drive select, and all that. Well, one of the pins is mini maxi, so I can put it in the mode. It's not automatic. The software must put it in that mode. Okay, so that means I can see what mode it's in right now, which is the whole point of this little tangent. So if we say, show me the mini status of status register 2, I can actually, give me the, up here. Status 2, IO port address 4. So I can say input 4. Okay. What does that mean? Status register 2. That's control register to status. So data request is off. 2-side, double density, index. What does that mean? 2 megahertz? A 1 indicates 4 megahertz, and that's what we got it set to. The CPU. Write protect. Well, the disk is actually sticking out of the thing right now. So this may not be terribly valid. 0 is write protect, and a 1 means it's writeable. Okay, that means it's writable right now because we got all 1s. Mini is true, and track 0 is true. 1 indicates we're in a 5 1/4. CCS uses this bit. Yeah, okay. So the bit 0 I see is track 0 if it's on a 5 1/4 because we just looked through that. All right, so I put the disk back in and do it again. The drive is still selected, by the way, the whole time. So that bit just flipped, the third one up, write protect. So 0 says write protect. Now, this actually makes a certain amount of sense because I have the write protect hole opened up. So that, I think, suggests that's working. The fact that we have a 1 in here, oh, it says high for an 8-inch drive. No, that's track 0. Okay. We're not over track 0 because I saw the head move. Oh, let's put it on track 0. Let's say, what do we need to do for that? We need to say, that's the Q command. We say Q. We give it the track number first. So I'll say 0, side 0, sector 1. And then we'll say read 1000, and we'll say, let's just read one sector, 11FF, because I don't want to sit here for an hour waiting for all of them. And it should fail, because it did last time, right? I didn't see anything happen. It's not making any noises. Maybe I got it all wanked up and we need to reset again. Okay, then we got an error. And it says it's on track 0. Well, it was on track 1, so maybe it didn't make a loud noise when I went to track 0. But my point is, if we input 04 now, we should be on track 0. What do we got? Track 0 is 0. Mini is 1. Write protect. Index, and we're double density, 2-sided. Okay, now the fact that we are on mini mode is very telling. I don't think this is going to work because of what we already talked about in the schematic. The fact that their discussion about it can use this track 0 to determine blah, blah, blah. I'm sure that if we look through the firmware, we'll find that it is sure and confident that this is a 5 1/4. Therefore, it's running at the bit rate of a 5 1/4 inch floppy. So it can't read that because the data is just going too fast. So we need to probably trick it by running our own firmware or hack something, or make an adapter and plug it into the 8-inch cable, or some jumpers or something to make it think it's got an 8-inch, because the 8-inch would have the right bit rate, which is kind of neat. So all right, so I put the 3-comp disk back in. Let's try the read again on track 0. Maybe it's not on track 0 anymore. I don't know. I suspect this is going to fail because in the oldie-timey days, CPM would record the first track as single density, even if the rest of the disk was in double density. And well, maybe it'll work because it did have that listed in here, right? Oh, died. Why did it die? Where's the table that we saw? There it is. Single oh. Well, yeah. If it, oh, okay. So, I think it's, yeah, I bet anything. It's trying to go in single density mode and not running in double density. I don't know. I think, okay, next time we need to look at the firmware source code. This is, something to be celebrated. This gives me great hope. This is really cool because it read, I don't care. It read off sector. We can make this work. It will work. All the hard part is done. As if there was an electrical issue or something like that, I would have no hope in getting this thing to work. So now I think we're at the point now where, wow, we can read stuff off the disk. And that would give us some way to get data into the machine if we really wanted to. But we can't use the Intel Hex uploader thingy because it's not supported in this version of the MOS. We need a disk that's reliable in order to do... We have one or the other, but not both at the same time. And that means we have the disk ROM monitor here that appears to be able to read stuff. You know what? We should try a write. Let's see what that's going to do. I'm going all for the gold here. Now, I've got some other floppies around here. One of which is, these are ancient. I'm never going to use them for anything else. I might as well keep these U.S. robotics discs. Maybe they're of value. I don't know. The other discs that I have are just old things that I have written files on. I think the one that I just put in there is a backup copy of like Word Perfect or something like that. It's a 720K. I set the write protect so we can write to it. Let's try this again. P191, Q101, read 1000, 11FF. Okay, it made the same tick sound. Ooh. Line space equations, blah, 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 EQA. Is that the same sector twice? Well, no, this is all one sector we're looking at. I can't get over the fact that it works. Okay, let's put some data in here. Let's fill 1000 to 11FF with 5A. D1000, oops, D1000, 11FF. Okay. Now let's write that out on this disk, right in the middle of that file. Where's the write command? Go. Actually, what we're going to have to do is reset the queue thing, right? I think I read in here somewhere that it picks up where it left off. So if you keep reading, it just reads the next sector, next sector. And presumably if I wrote UV, how do you write to this? Oh, there it is. Set by the P and Q command. Mind your P's and Q's before doing where this is if the address end is reached before a sector write is completed, it'll complete read data until it fills the disk anyway, which is fine. Please note double density requires that. And I think they mean double density on an 8-inch, which is the same clock rate, as I said repeatedly, as the 1.4 meg. So this should still be viable if we can figure out what's wrong with the firmware. Okay, so we have to mind our P's and Q's, right? So let's do another Q101, and then we're going to do a write 1000 to 11FF, and put all those 5As onto that first sector of track 1. Okay, Q101. Read. Well, this isn't going to be. I have to fill 1000 to say 2000 with 88s. Okay, D1000, 11FF. Now, let's read 1000, 11FF, and we should get our 5As back if we get a bunch of text. Then it will have broken. Moment of truth. Let's not go there. Let's go from D1000 to 20FF. So we'll go a little past. Ooh, that's too much. D1000, 12FF, which means we'll see all of the sector plus a little garbage afterwards. So we know that it, like I said, if it's not big enough, it could have kept going or something like that. Oh, and it read the 5A. Oh, baby. We wrote that on there. Wow. Let's think about this. Let's go back to Q101. Read 1000 to say 2000. Let's read that and more. Okay, oops. If I remember to D1000 to, let's say we go to D1 400. Awesome. So we just corrupted the disk, but it worked. We can read and write. Oh, this is great. Oh, baby. Provided that it's only running on a 720K floppy, we're good. I think I need to think about this. That's what I need to think. Next time, let's look through the source code of the firmware that I saw at the bottom of this manual. It's just like the CPU firmware. They give you the source in here. And we can see what there it is. We can look and see what they did in here and see how they operate the drive. And maybe, I don't know, glean something or figure out how to make the other. I'm real excited about. I want to be able to make the 1.4. I don't know why. I'm hell bent on reading this AOL floppy disk for some reason. I think we can make this work. This is going to be really cool. We should be able to write a BIOS and everything. We should be able to boot CPM on this thing off a 3.5-inch floppy. All right. Well, this is somewhat of a qualified success, I suppose, but I'm not surprised that the 1.4 didn't work because of the way those wires are hooked up in there. So, I mean, this is an almost qualified success. I declare this all positive news today. So this is great. Absolutely great. Definitely a worthy little project here. This is going to be cool. I can't wait to see me load software and run it off the floppy. This is going to be great. So now what we need to do is figure out how to format track 0. Oh, well, we need to see what's going on with the firmware. I'm so excited. My mind's all over the place. Next time, I don't know what we're going to do, but it's going to be super cool. Thanks for watching. I'll see you on the internet.